In the previous video, I was mainly validating the topography data that's used by SW4 uh, is indeed identical to the topography data that I wrote into the R file. So I was basically just comparing the input topography uh, with the topography output file that's created by SW4's image command. Right. Um, so 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 I was what I was doing. Uh, so I was creating the so test.in, that's the input file for SW4. That's like the master input file for controlling the behavior of SW4. And then in this particular section, I was trying to ask SW4 to write out the actual topography data that was used by SW4 by using those kind of image keywords, right? So I was sort of trying to write out the topography data. Topography data has to be written for z equals to 0.0. Z equals to 0 means that I want to extract the data at free surface, right? And the mode that I want to extract is topo. And then I also want to extract the latitude and longitude so I can have a horizontal axis for making the plots. And then the MATLAB script for plotting the topography data is kind of summarized in this topo underscore SW4 underscore plot .m file. And then I need to add the path. And then I use the read image that's provided by SW4 to load the output data that's created by these three commands. Basically, they are just these output files, right? So with this kind of suffix .sw4img, with this kind of suffix, so topo, this particular file was created by using this image command, right? And then the lat and the long creates these two output files respectively. And then all I have to do is to use the read image MATLAB function provided by SW4 to load those data into my workspace. And then I loaded some additional data, and then I can just make a plot. Right? I can just make a plot using the right projection, the correct projection, and then surf m is sort of one of the functions in the MATLAB's mapping toolbox, and then I can just compare the topography that's created by this image command with the input topography that I wrote into the .r file, right? So in this video, I will try to sort of validate the velocity model that was so the velocity model that's written into the R file should be identical to the velocity model that's used by SW4 in its calculation. So in order to actually write out so the velocity model is essentially a volume, right? It's a three-dimensional volume. It's no longer just like topography. Topography is more like a surface, right? But the velocity model is a volume. It's a three-dimensional volume. So you can look at this kind of three-dimensional volume either using map view plots, like this kind of thing, right? You're plotting a two-dimensional cross-section, which is a kind of a horizontal cross-section, right? That's called the map view. Or you can actually make a cross-section view that's kind of vertical, right? So um, so in SW4 you specify these two kinds of outputs using two different using using the image keywords, right? So here what I'm trying to do is to actually create a horizontal or map view slices or two-dimensional map view slices at z equal to 0, which is supposed to be topography. So it's a free surface, I mean the free surface. And then mode equals to s means that I want to output the vs, the shear velocity. This is at 10 kilometer, 20 kilometer, 40 kilometer, 60 kilometer, 80 kilometer, 90 kilometer, right? And then that's what I wanted to sort of look at, right? Let long is already sort of written it's this output is already created, and then all I have to do is to create those additional map view images. And then if I want to look at the cross sections, so here I'm looking at the cross section of S again, VS shear velocity again, um, at two cross sections. One is at x equals to 512, and then the other cross section is at y equals to 1000. These two cross sections are sort of more or less in the middle of the entire volume, right? So the y dimension is like a 2000. So um, uh, the y dimension is like 2000 meter, 2000. No, I think I got it wrong. I think it's y equals to 1000. Uh, oh, this is not really grid points. This is actually in terms of meter, I think. Or is it in terms of grid points? Let me take a look. Image command. Oh, that's file formats. Keywords. Image, right? So x location of image plane. So it's in terms of meters. So x, y, z are supposed to be meters. So I guess this is not grid points. Uh, so I was trying to create an image. That's the cross sections are created is not really in the middle of the volume. So this is in x is like a x in x direction. I have like a 1000 grid points, and the grid spacing is close to 1000 meters. Uh, so this is at 512 meters. So it's actually very close to origin. And y equals to 1000. That's y equals to 1 kilometer. So this is the unit is meter. So this is also very close to origin. But nevertheless, it's gonna be a vertical cross section. It's not really a map view plot, right? And then I also want to look at if I want to. So mode is still S, right? But the thing is that for this kind of vertical cross sections, I need to actually output the grid. So if I am outputting at the VS at a X cross section, then the grid is supposed to be in the Y and the Z direction, right? So if I am sort of writing out the cross section, the VS cross section at a Y equals to 1000, then the grid is supposed to be for the X and the Z direction, right? So it's important to actually write to give it a mode equals to grid so that I can get a grid, so I can sort of write out so I can make a plot later on, right? Yeah, so I have to remember this is for meters. This is not really grid number. It's meters, right? So these two sets of image commands allow me to actually look at the shear wave velocity model at map view and different cross sections. But the problem is that those map view plots created by SW4 seems to be inconsistent with my actual input. So the problem that I have found is that if I use those image files created by SW4, the image files are written into SW4 test. So it's actually these kind of image files, right? Those image files. Those are the image files actually. But the problem is that those image files for z actually equals to different depths are actually giving me identical velocity, right? And all the images created at different z are actually identical to the map view plot for z equals to 0, right? So this is a z equals to 0 for s velocity, right? And then this is z equals to 10 kilometer, s velocity at 10 kilometer. This is s velocity at 20 kilometer. This is s velocity at 40 kilometer. And all of those velocity models, all of the plots are actually identical to the free surface. So this is let me suppose I change the depth to 0, right? So this is the Malevich script that I that I put together to actually read those image files created by SW4. Right. So that's called a VM underscore map underscore SW4 underscore plot. So if I run this one, right. So this is actually more or less like the shear velocity at free surface, right? But now if I change it to like a 90 kilometer, right? That's 90 kilometer. If I run it again, 90 kilometer, that's like oh, I see. Um, but if I change it to like 20 kilometer, right? 20 kilometer. Uh, that's like identical, right? The, this kind of problem that I see is that only happens in the curvilinear grid. So SW4 is gonna give me is gonna construct like two different grids. On the top is a curvilinear grid that's gonna account for um, topography, like this kind of thing. If I look at the cross section, the top grid is the curvilinear grid, right? And then the lower grid is like the usual uniform spacing finite difference grid, right? So if my map view cross section is within the curvilinear grid, then the velocity model that I'm getting from the image command is always identical to the velocity model that's at the free surface. For some reason, maybe I'm not using it correctly, but that's what I found so far. Maybe later on I can discover why, but this is something that's quite strange. Um, right. So 20 kilometer is still within the curvilinear grid. The reason that why it's uh, so if I look at my test in the master input file, Z max equals to 33 kilometer depth, right? So and then when I run this code, when I run SW4, it's actually telling me that the curvilinear grid is actually down to like 35th grid point. So if I 35th grid point, that's about um, so if the vertical grid spacing is on average is like 950 meters per second, if I multiply 35, 35, 34, 35, that's close to like 33 kilometer, right? So Z max is gonna tell me what's actually the depth at which I transition from the curvilinear grid to the uniform grid, right? So this transition for my mesh, this transition actually happens close to like 33 kilometer depth. So for z equals to 0, that's the free surface, and also for z equals to 20 kilometer, both of them are inside of the curvilinear grid, right? And then if that's the case, then the the map view image produced by SW4's image command is always going to be identical to the velocity model that's at the free surface, right? So that seems to be something um, quite strange, right? So, but that's okay. That's okay. That doesn't actually that's not really a serious problem. It's just a plotting problem. I think it's something that's kind of associated with the image command, or associated with how the uh, how the image is produced. The truth is that the velocity model that's used in the SW4's calculation is still the correct velocity model. Why do I say that? It's because if I actually dump out the velocity model as a three-dimensional volume, and then try to actually read the entire volume into the into the into MATLAB and then make the plots, and then you'll see that they are actually very very similar. Right. So this figure one, this particular plot is actually the velocity model that I wrote into the .r file, and then on this side of the plot, it's actually the velocity model that's actually used by SW4. It's something that I dumped out during the before the time loop in SW4. Right. They are plotted in the same color scale. So the velocity model that I wrote into into the .r file uh, is like that, right? So that's the Southern San Joaquin Basin. So Sierra Nevada batholith, right? And then you have low velocities close to the Cascadia, right next to high velocities, right, of the Cascadia Mountains, and then you see identical features, right? And almost all, even the shape of the anomalies are actually identical. There are some differences, right? So if you look at this corner that's actually not covered by data, um, you see some differences, right? Um, this image was created just by extracting uh, a constant grid point, a constant vertical grid point, right? But a constant vertical grid point is not exactly 20 kilometers below topography, below free surface. The reason is because of the vertical grid spacing. The vertical grid spacing in the curvilinear grid is actually variable. So at different lateral locations, the vertical grid spacing is going to be different inside of the curvilinear grid, right? So if I actually extract a constant grid number, right, a constant vertical grid number, say and subtract iz. Iz is 9 here, right? So and that's like the last uh, vertical grid. So when I actually loaded this kind of particular data, I actually sort of reversed the vertical axis, right? So SW4 has the vertical axis that goes into the Earth, right? But when I loaded this data, I actually reversed the vertical axis, right? So now the first grid point in z direction is going to be uh, at depth, and then the last grid point and in vertical direction is going to be at the free surface, right? Um, the reason that I want to do that is because when I do the inversion, I want to reuse some of the codes that I wrote for AWP, and AWP actually uses a coordinate system that has a vertical axis that's pointing towards the free surface, right? And then the coordinate system is also right-handed system for AWP, uh, so that's one of the things that I need to pay attention to. For SW4, x-axis is like that, y-axis is like that, and then z goes down, goes into the Earth, right? But after this kind of a coordinate transformation that I did, x goes this way, and then y goes this way, and then z goes up, goes pointing towards the free surface, pointing out of the screen, right? So that's some of the differences, right? So and then a constant z grid point doesn't actually mean a constant depth, right? Because the vertical grid spacing keeps varying, keeps changing across the entire curvilinear grid, right? So that's going to introduce some kind of inaccuracy. So ideally, I should try to actually do an interpolation, right? I should try to do an interpolation, interpolate it to a constant depth below topography, right? But for this sort of very quick validation, quick and dirty validation work, I didn't actually do that, right? So in principle, I should do that, but it's a step that I skipped, right? But nevertheless, because of the topography compared with the entire vertical entire vertical depth, which is close to like 100 kilometer, the topography variation is actually negligible. It's not really that big. So that's why these two images actually match pretty well. Right? Actually matching pretty well. Right? There are some slight differences, but in general, the pattern are actually identical. Um, right. So so how did I actually dump out all the velocity model, right? Dumped out the entire three-dimensional velocity model that's used by SW4. There are a few steps. There are a few steps. Um, so now this test.in file is like the master input file that's gonna be read by SW4, right? But I added another input file that's called imv.in. So for now, the file name is like hardwired, so it has to be this particular file name, imv.in. That's kind of the input data that's kind of specific to the inversion or tomographic inversion. So the format of this particular file is for at least for now. For now, it's got like a few lines basically. Uh, so uh, the first line is controls the level of output the level of output data, what kind of output data is going to be written. So for now there are three choices. Three choices. If it's 0, then when I run SW4, SW4 is going to create. When I run SW4, it's going to create uh, output files that's kind of describing the mesh, right? So if I look into the output file directory, SW4 test, there are a bunch of outputs, right? So if the first number is 0, then what it's gonna create these files, these .info files, which basically describes the setup of the mesh, right? These files, and then also these files that starts with Z. That's basically the vertical grid spacing, the vertical grids for different processes. So this these files. So if I take a look at the one specific example, SW4 test. Oh, I'm gonna look at the last one. These files are pretty simple. It's just describing each the grid number on each of the processes. So SW4 is the parallel code, so it can run on multiple processes. And then the entire simulation volume is partitioned into those multiple processes, right? So how it's gonna partition the entire mesh, right? It's gonna partition the entire mesh in a two-dimensional way. So so it's not gonna try to divide the entire mesh in the vertical direction. So every process is gonna do the calculation for a portion of the grid that's divided laterally, right? So every process is gonna process all the depths, but it's just a subset of horizontal grids, right? So that's why I have only 6 digits to label the processes. This is something that's kind of different from AWP. AWP allows you to actually partition the mesh also in the vertical direction, right? But this SW4 only allows you to actually partition the mesh in a two-dimensional way, in the lateral direction, in the two lateral directions, right? So this is process 0, 0. Process 0, 0 is gonna process a portion of the mesh, and then process 0, 1, right? So the first 3 digit is for the process ID in the x direction, and then the next 3 digits are for the uh, process ID in the y direction. So in this particular example, the entire mesh is partitioned into like 8 processes, right? Because in the x direction, it has like two. It goes from 0 to 1, right? So it's like 2 processes. And then in the y direction, it goes from 0 to 3, so it's like 4 processes. So 2 times 4, that's 8. So 8 processes, right? Um, and then each process is gonna do calculations on a subset of the entire mesh. So if I look at the last process, which has a process ID in the x direction, it's 1, and in the y direction, it's 3, right? Then its content is gonna look like that. So the number of lines is identical to the number of grids. So in this particular cross section in the user manual, it's got like 1, 2, 3, 4, 4 different grids, right? Because of its using different kinds of refinement, right? But here I'm actually not using any kind of refinement command. So I only have like 2 grids, because the curvilinear grid is always one separate grid, right? So if I look at this particular output file, zeroth grid is like the grid that's kind of close to the bottom, right? And then the last line, the last row inside of this file is for the top grid. That's the curvilinear grid. So it goes from bottom to top, right? So the bottom grid is listed at the bottom, and then the top, the bottom, the no, I think I said it wrong. So 0 is, this is the bottom grid. It goes from bottom to top. Goes from the bottom to top, right? 0 is like the bottommost grid, and then 1 is like the grid that's on top of the bottommost grid, right? And then the last row is supposed to be for the curvilinear grid. So in this particular case, process 1-3, or CPU core 1-3 is gonna process uh, 2 grids, 0 grid and the 0th grid and the first grid. The 0th grid is close to the bottom, and then the first grid, that's the curvilinear grid, right? And then it's gonna process the range of the x coordinate. That's gonna go from like the range of the x grid number is gonna go from like 501 to 1000. And then the range of the y coordinate, y grid number, is gonna go from 1564 to 2084. And then the range of z coordinate is gonna go from z grid number is gonna go from 1 to 61. Right? That's for the 0th grid. That's the bottommost grid. And then go from 1 to 35. That's the curvilinear grid. Right? So it's gonna process all the grid points in the z direction, but it's just a portion of the x and y grid, right? So that's why it's a two-dimensional partition of the entire mesh, right? So these files are like text files. We can read it, but those z files are actually binary files. So its content is actually not readable directly, but we can write a code to actually read it. So